Good day everybody, we got an interesting question. I'm going to write the question down so that you will be in a better position to visualize the question's configuration. So I will mention that we have the integral sign and then we have a huge square root. Inside the square root you have an x. Now after this x there is immediately another square root and you have an x, but the only thing is that in this case the exponent is going to be 1 over 2, right? So in other words, I have to place 2 here, and let me just explain to you. If you were to write root of x, then this is nothing but x raised to the power of 1 over 2. You can either write it like this, or you can go a step further and write it like this, with the 2 being placed inside the wedge. Okay, and I have mentioned to you that if I were to place 3 there, then this is nothing but x raised to the power of 1 over 3. So that is the idea that we are actually bringing here. So this is going to be x, and inside this wedge you have 3. So you got the x here. Now this x is actually sheltered by this root, third root. We call it as a third root, and then it is sheltered by the square root. Now this is followed by another square root, and you have a x. Now this has inside this wedge as 5. So this is sheltered by this third root and sheltered by the square root. Now this is followed by another square root, and you got an x there, and this should be 4. Now let me just, it's not 5, this is 4 here, and you got 5 there. Now this is followed by another square root, which is represented as follows in this manner, and then inside this wedge it has got 6. So the representation goes on. So I will just place a square root like this, and then I will just place 3 dots. So that means it's just continuing on. So in this case it's going to be x, and the root is the value that has to be placed inside this wedge is going to be 7, and it goes on, and this entire component has a dx. So this is the representation. Now we will have to integrate this. Okay, so one of the reasons I made this question, or in other words I wrote this question out, so that you will be able to visualize that if you were to consider this, then this is sheltered by the 6th root, 5th root, 4th root, 3rd root and square root. So you can just place the 2 there. Now you will be able to successfully integrate this only if you can make the representation as follows, otherwise it's confusing. Now let me take the first root, or the first quantity. The first quantity is actually x, and on the top of x you have 1 over 2. Okay, fair enough. Now that x which we have just represented here is multiplied by another x which has got 1 over 3, and on top of it you got 1 over 2. So I'm going to place it like this, 1 over 2. Okay, I hope you're able to understand what I am actually writing here. Now this is followed by the next x, and this has got 1 over 4. So you just place 1 over 4 on its head, and this 1 over 4 is sheltered by 1 over 3, and subsequently it's sheltered by 1 over 2. So you have the representation like this. Now if I were to extend the x's, I would be having something of this form. So this is equal to x raised to the power of 1 over 2. There is a law in indices, a raised to the power of n times or in other words a raised to the power of m raised to the power of 1 over n. This is rewritten as a raised to the power of m times 1 over n. That's going to be m over n. Okay, so by that, subsequently I can also have a representation like this. If I were to have a raised to the power of 1 over m, that is raised to the power of 1 over n, this is going to be a raised to the power of 1 over m into n. So this is going to be x raised to the power of, now I can either multiply this by 1 into 3 into 1 into 2, but I do not want to do that. I want to have a representation like this. Okay, so this is going to be 1 over 2 times 1 over 3, but anyway I will just I'll just place 6 there. Okay, now this is followed by x raised to the power of 1 over 4 times 3, 12, 12 times 2, 24. So just place 24. This is followed by, now this is 4, 3, 2, this is 3, 2, 1, and this is 2 times 1. So you can just assume it like that or take it like that. It's not going to affect our understanding or the representation of the problem. Now the next one is going to be 5 times 4 times 3 times 2. So that's going to be 5 into 24. So 22, 5 times 2 is 10, and then you got 120. So you have 1 over 120, and this thing proceeds, goes on. So therefore, if I were to place the integral sign, this is exact representation that we have. Okay. Now what I want to do is I would like to draw another law in indices. So this is multiplication, this is multiplication, this is multiplication. Now that law is, if you have a raised to the power of m and then you are multiplying with a raised to the power of n, the bases are same, then you can rewrite this as a raised to the power of m positive n. Okay, so by this what I'm going to do is I'm going to rewrite this as integral x raised to the power of 1 over 2 plus 1 over 6 plus 1 over 24 plus 1 over 120, right? And so on, multiplied with dx. Fine, fair enough. Now 6 is 3 factorial, now 2 is 2 factorial, and 24 is 4 factorial, 120 is 5 factorial, and so on it goes. So I can rewrite this as integral x raised to the power of 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial plus 1 over 5 factorial plus etc. times dx. Okay, fair enough. Now let me go to the next I hope I got a next sheet. Okay, so this is equal to, let me rewrite that, integral x raised to the power of 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial plus 1 over 5 factorial plus etc. times dx. Now there is a beautiful expansion, Taylor series expansion for e raised to the power of x. Now if you were to go and check that expansion out, that expansion would be as follows: e raised to the power of x is equal to 1 positive x over 1 factorial plus x squared over 2 factorial plus x to the power of 3 over 3 factorial, x to the power of 4 over 4 factorial plus etc. That's a Taylor series expansion. Now when x is equal to 1, you get e raised to the power of 1 is equal to 1 plus 1 over 1 factorial plus 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial plus etc. Right? Now we have 2 factorial, 3 factorial, 4 factorial, 5 factorial, etc. 2 factorial, 3 factorial, 4 factorial, and 5 factorial, etc. So this can be rewritten as e negative 1, I'm bringing this to the other side, negative 1 over 1 factorial. This is equal to 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial plus etc. Okay. So in place of this, I will substitute this. Now what is this? This is e negative 1, negative 1. That's e negative 2. Okay. Now go back here. So this is going to be integral. In place of all of this, I'm going to substitute e raised to the power of, we should say x raised to the power of e negative 2. So in place of all of this is going to be e negative 2. That's exactly what we found, right? You see here, so go there and substitute that. This is actually accompanied with the differential operator dx. Now this is similar to our popular integral formula, x raised to the power of m times dx. Now what do we get when we integrate this? Nothing but x raised to the power of m positive 1 divided by m positive 1, positive arbitrary constant c. This is the popular formula. So this is going to be x raised to the power of e negative 2 positive 1 divided by, this has to be divided by e raised to the power of negative 2 positive 1, which is rewritten. I just want to complete it over here. So this is equal to x raised to the power of negative 2 positive 1, that's going to be e negative 1 divided by e negative 1 plus arbitrary constant c. If you don't place this, the solution is not complete. So that is the end of this beautiful question. Please like, share and subscribe to our channel. Thank you everybody.